Надеюсь, YouTube включил.
Сейчас.
So today we will discuss Hodge structures. First, just as an abstract linear algebra notion, and then we will discuss some, and then I will try to illustrate why this notion is so important. So I will just formulate some theorems, some already theorems, but of course we will discuss proofs of these theorems later. But first of all, just an abstract notion of Hodge structure. So suppose that we have the model of finite rank or finite dimensional vector space, Q vector space, or finite dimensional vector space. Then we can consider VR, that is just in the product with R and over complex numbers. And here we have a real structure. Here we have a conjugation. There is a conjugation. We will denote it just by V maps to it's conjugated. And now definition. So an integral Hodge structure of weight n. So an integral means that we consider a free Z model, and there is also a rational Hodge structure. This is for finite dimensional Q vector space. We will discuss in a minute examples. So what is an integral Hodge structure of weight n? First of all, this is Z model V. With the following decomposition of its complexification. The direct sum of PQ, where P plus Q is equal to n, such that the complex conjugation of PQ gives you Q. Okay, and rational Hodge structure. This is the same thing, but for Q vector space. Of course, the main example of Hodge structures is Hodge decomposition of smooth scalar variety over complex numbers. And an integral Hodge structure is cohomologous with Z coefficients, and rational Hodge structure is cohomologous with Q coefficients. Okay, and we say that two Hodge structures are isogenous if the corresponding rational Hodge structures are isomorphic. So, of course, for an integral Hodge structure, we can consider the corresponding rational Hodge structure just tethering by Q. So there is an obvious notion of isomorphic Hodge structure, and we say that there is a genius if the corresponding rational Hodge structures are isomorphic. So let me give an example. How does it work? For example, consider two elliptic curves. Elliptic curves, and suppose that we have a double covering of between them. Yes, then this double covering, what is the ramification of the corresponding double covering for an elliptic curves? Yes, it is. Then it's unramified, right?
What is C prime?
Elliptic curves, two elliptic curves. I just want to illustrate the notion of isogenous. What does it mean? So suppose we have two elliptic curves, and suppose we have a double covering between them. Then by Hurwitz formula, this double covering is unramified, right? Then what we have on the level of integral cohomologies? If we have a double covering, we can consider the corresponding map of first cohomologies. Then for a double covering, this will be an embedding of index 2, right? So, right? But it's easy to see that their induced Hodge structures are isomorphic in this case. Isomorphic Hodge structures. So this means that their corresponding first cohomologies are isogenous Hodge structures, right? But the corresponding integral Hodge structures are not isomorphic, because here we have an embedding of index 2, right? On the level of rational Hodge structure, this is an isomorphism, but on the level of integral Hodge structure, no. Okay? So, and now, let me explain the notion of Hodge classes. So if we have a, suppose we have a Hodge structure, of weight, of some even weight, okay, then Hodge structure 1. Then the intersection of V with KK is called Hodge classes. This is Hodge classes in V. Here I use an obvious embedding of V into its complexification. Okay? Note that, in fact, here I should use this notation. Note that, for example, this thing can be empty. We saw this on the level of Picard group, right? So we already discussed that for a K3 surface, for a complex K3 surface, its intersection with 1,1 cohomology, intersection of H2 with integral cohomology can be empty. With 1,1 cohomology can be empty for a non-projective K3 surface, right?
Oh, should be 0?
Hmm?
Just 0 instead of empty.
Yes, yes. So 0. Okay. In particular, this is, of course, for an abstract Hodge structure. If we consider its complexification, this is something proper. Proper subspace here. Okay? But if we consider VR intersecting with KK and then take its complexification, then this will coincide with KK. And similarly, if we consider VR intersecting with VPQ of direct sum QP, and then take its complexification, then we obtain this direct sum. Okay? So this means that this direct sum is in fact defined over rational numbers. We have already discussed this, right? Just because they are conjugated. We can consider this is something defined over rational numbers. And this is always defined over rational numbers.
To write this, we need to complexify BKK, yes?
What?
I mean, in a basic proper, you mean that...
I mean that if we just take intersection with integral,
yeah. And then
we'll complexificate. Of course, because otherwise...
The right-hand side should be complexificated too, yes?
Here it's always complex vector spaces. Maybe I didn't say this. When we have a Hodge structure, we have decomposition into complex subspaces, such that they are conjugated. But they don't have real structure. And what I'm saying is that if we consider direct sum of PQ and QP, then this will be defined over R. Okay? This is abstractly. This is just we see is a direct sum of complex subspaces. This is complex.
The question here is, why is that the proper subset of BKK?
Why this is a proper? Why it doesn't it doesn't coincide with KK? So this is an example for even for classes of 1,1 type. Okay, as we saw in the if we have a complete. So we discussed that Picard number of a K3 surface is something between 0 and 20. So and this is something 20-dimensional. So if this is less than 20, then we obtain a proper subset, right? Because here we should take intersection with integral part, okay? And here we take real part, okay?
Is it always proper?
No. If we have a maximal Picard rank here, right, then it will coincide. This depends on how big this is this intersection. Sometimes it's maximal, but sometimes it's just 0. Okay. And now it seems that's okay that I decided to discuss all this notion in a detailed way. Okay. Now a definition. We say that sub, and in fact, why I want to discuss this in details, because for Torelli theorem we need for Torelli theorem we need Hodge structure on the second cohomology of case-3 surface. Okay, so sub-Hodge structure of structure V of weight n is a submodel or Q vector subspace submodel V prime V or Q vector subspace such that complexification of V prime the decomposition of complexification of V induce the decomposition of complexification of V prime. So it's decomposed in such a way. And it's very easy to give an example of sub-Hodge structure if we take any Hodge class then it gives you a sub-Hodge structure. Sub-Hodge structure. And the space, and of course the space of all Hodge structure too, of all Hodge classes also gives you a sub-Hodge structure. Okay, this is an example. And now, let me also say that sub-Hodge structure is primitive if for an integral Hodge structure, if this quotient is torsion free, and we will say that Hodge structure that does not contain any non-trivial proper and primitive for an integral. Here for integral Hodge structure. Integral. Hodge substructures. Structures is called irreducible. reducible Hodge structure is very easy to give, so you can just consider first cohomologies of an elliptic curve. Then, so for an elliptic curve, this is decomposed in a and this is what vector spaces? This and this. Generally, for any curve or any smooth curve, of genus G, this is what? H01 or H10. This is what is its dimension?
G.
Here we take CG. So here is C plus C, and it's easy to see that we just can't take sub-Hodge structure here to obtain something in such way. Is this clear? If it's not clear, this is an exercise why it's primitive. Just by more or less by definition, it's primitive. So this is that in what dimension for an elliptic curve?
2.
This, so if we take any one-dimensional sub-model here, right, we will obtain C, and it cannot be gives you this decomposition. Okay, this is an example of irreducible Hodge structure. And then and now let me give an maybe at first glance a bit strange example of Hodge structure, but it's in fact it is used everywhere. This is so-called the Tate Hodge structure. Of course, this it will be also irreducible. This is denoted by Z twisted by 1, and this is free Z model of rank 1. In fact, its embedding is given by 2 pi I Z in C. This is from here it's not obvious why we use this 2 pi I, but this comes from complex analysis. Okay, and this is a Hodge structure of weight -2, such that Z1 minus 1 minus 1 is one-dimensional. And we will discuss later why here it's why convention is so that twisting by 1 corresponds to -2 here. After we will discuss what is the morphism of Hodge structure. So this is a very easy example of free model of rank 1 and of a weight -2. And now let me also now we discussed just some linear algebra notion, but I hope that in the end of the lecture you will see why this notion are important, and I hope I will be able to explain you motivation for all this linear algebra thing. Okay, and now let me also explain some standard linear algebra constructions that we can apply to Hodge structures. So first of all, we can consider direct sum of two Hodge structures. Direct sum of V and double V. This is of weight n, and this is of weight m. Then it's of weight n. They both are of the same weight. This is direct sum of PQ. Okay. Also, we can consider tensor product of two Hodge structures. Here we can consider a different weight n. Weight n, and this will be Hodge structure of weight n plus m. We say that its PQ part is the direct sum of tensor products Q1, Q1, 4 times Q2, where P1 plus P2 is equal to P, and automatically, of course, we will have zigzag. Okay, this is a definition of a tensor product of two Hodge structures. Then we can define dual Hodge structure. So if this is of weight n, then its dual is of weight minus n. By definition, as Z model, it's a home from U to Z, and we do minus P is just home over C from PQ to C. So this is something inside dual space. Okay, and now let me explain just and now let me explain how does it work in the case all this in the case of Tate Hodge structure.
Sorry, by the way, in Hodge decomposition, P and Q may be just arbitrary integer. Yeah.
Yes, right. But of course, for complex, for Kähler manifolds, they are positive. But abstractly, we can define them in a such a way. So this is an abstract notion. It can be non-positive. Okay, an example. So that -2 is just by definition dual to Z twisted by 1, and this is a Hodge structure of weight 2. And similarly, twisting by K is just tensor product of Z1 for k positive and -1 for k negative, and this is always of weight -2k, and by convention Z0 is trivial of weight 0 and rank 1. Okay, and for an integral or rational Hodge structure, we can define a twist. So for V of weight n, we can define a twist just by tensor product of V with zk. Or yes, of course. And here we can consider also a rational Hodge structure just by tensoring by Q. So this is a twist, and this is of weight n. What is weight of this Hodge structure?
And -2k.
N minus 2k. And now you will understand why we use this convention, just because this is Q plus k. Okay, for the twisting Hodge structure. Okay, and now let me define a morphism of weight k. So suppose V and W are Hodge structures of weight n and m. Then a morphism of weight k is the morphism of the corresponding Z models, that is Z or Q vector spaces, that is Z or Q linear, such that its C-linear extension satisfies. What do you think it should satisfy? Where an image of VPQ should live if we want to define something of weight k in W? Plus k, q. So we just so it's of weight k. We have such a сдвиг. No ладно. Okay, if we have this condition, or equivalently, this is a morphism of this of weight 0, right? Or this is just a usual notion of morphisms between two Hodge structures, but here we need to consider twisted Hodge structure W, okay? So in this case, M should be equal to N to K, so K is defined from M and N, so sometimes we just, usually it just omitted. Okay, and an exercise, just to understand these notions better, it's very easy. It immediately follows from what we follows from definitions. So I will denote by this letter morphism of Hodge structures of weight n, of weight k. Morphisms of weight k. So I claim that this is an intersection. So this is Hodge classes into this Hodge structure. Okay, so this is isomorphic to Hodge classes in this Hodge structure. Okay, so we discussed the notion of dual Hodge structure. We discussed notion of tensor product of Hodge structure. So this is the Hodge structure of weight 2k, and we just take Hodge classes in it. And the exercise is to show that this gives you morphisms from Hodge structure V to Hodge structure W of weight k. Okay, so as in linear algebra. Okay. Yes, and also let me say that also we can define exterior product of Hodge structure. So if V is of weight n, then its exterior degree is of weight Kn, and we say that EQ is the sum over all tensor products V.
Sorry, I don't understand the right hand side why you want like 2 copies of the dual tensor respectively.
What? 2 copies. Wait, this is a Hodge structure, right? So if we have 2 Hodge structure, we can define dual Hodge structure and its tensor product, right?
Yeah.
Its weight will be 2k, so we can consider Hodge classes in it. Okay, and what I claim that Hodge classes in this Hodge structure gives you morphism of weight k, and vice versa. So this is an isomorphism. So this is just an inequality. And this exercise immediately follows from definitions, but you need to read definitions carefully to get more comfortable with them. Okay, and here of weight Kn we take sum over all. So the sum of Kn is equal to k, and Ka by A is equal to P. So let me illustrate what's going on for Hodge structure of weight 1. In this case, its second exterior degree is something of weight 2. So what will be 2, 0 by this definition?
Just a second. So Q and QI doesn't matter in this decomposition?
No. Ki by I should equal to P.
And how about Q? We don't care about Q.
Q is Qi is n minus pi I. It's defined from weight n.
Ah, yes. Okay.
So what's this? Sorry.
First, it's just
Lambda
the
2, 0.
the 1, 0, and nothing else.
Yes. And what is 1, 1?
The 1, 0 actually 0, 1.
But in this case, it's not weight, it's just tensor product.
Yes.
And
Why don't we have 0, 1, tensor 0, 1?
okay, this is an exercise, okay? But just from this definition, you will immediately obtain this, okay?
No. Leo means twist the order with 0, 1 and V1, 0. I think they should be the same.
It's the same, of course, but I didn't understand the question. We have on
Yes,
this,
we do.
okay? And why why this notion of exterior product is important? So, for example, if we have a complex torus, then, so let me denote it by A. Then what is its first cohomologous? In terms of lattice.
That is not the real.
This is just dual lattice. And in fact, H2 AZ is isomorphic to what in terms of H1? So
Lambda 2 of H1.
And this is in fact an isomorphism of Hodge structures. And here, in fact, we can write any n. So this exterior product of Hodge structures is important, for example, because for a complex torus, we obtain its Hodge structure on its cohomologous just as an exterior product of Hodge structure on the first cohomologous. Okay? And now, yes. And now let me also. Ой, как много времени прошло. Okay, let me also define complex conjugate. Complex conjugate. Hodge structure just as a conjugate. Complex as by definition, its PQ is equal to QP on the Hodge structure that we considered before. Okay, and now also let me say that Hodge structures of weight n can be equivalently defined from Hodge filtration. Hodge filtration. That is the following thing. So suppose we have a Hodge structure of weight n, then we can consider the following filtration on Hodge structure V on its complexification. N zero. Where this is a direct sum of PQ, where P is greater or equal to I. Okay? Then what we have? We have for such a Hodge filtration, we have the following, it has the following properties. If we consider its
I don't understand the notion for FNVC. Because
it just so this is just n0 for n. It just n0.
it's just Fi. Is that operator or something?
No. This is just a subspace. Fi. This is a filtration. So we take a complexification of the corresponding Hodge structure, right? This is a vector space over C, and then we consider убывающее. Как сказать убывающее? Decreasing. Decreasing filtration. So this means that we consider its complex subspaces that are.
I understand, but so probably there you want to write FIVC or.
Yes, here, yes, of course.
Okay.
And so here I just define what is this complex subspaces. This is just a direct sum of VPQ, but P should be greater or equal to I for a fixed I. So this is decreasing filtration. So for example, phi maximal, its maximal term is just consists from complex space N0, right?
Yes.
Okay, and so on. Okay, and now what we have here? Here we have the following property. If we consider this complex vector space, direct sum with the conjugated complex space, where P plus Q is equal to N plus 1. So if we take two numbers P and Q such that their sum is equal to N plus 1, then we have the following property. If we take this complex subspace, and if we take its conjugated, and this complex vector space, and take this its conjugation, then we obtain the whole vector space. Okay, and in fact, this notion, and in fact, here we have bijection. I mean that if we have a filtration on a complex vector space with real structure, that is, on this vector space we can define conjugation. Yes. So suppose we have a complex vector space with conjugation, with a filtration that defines has the following property, right? This property. Then from this thing we can define Hodge structure of weight n just by letting P n minus P be an intersection of V C intersection with n minus n minus p with c conjugated.
But it's only complexified part. We also need a lattice.
Uh, I think that we can obtain lattice just from real structure.
And we also completely forget about torsion.
About torsion?
We don't have.
We don't have torsion.
Don't we?
It's free Z model. When we obtain
yes, okay.
it's free Z model. Сейчас. Okay, yes, maybe we also should. So, okay, maybe we need to take lattice here. I'm not sure, I will answer definitely maybe next time, but yes, we should take a lattice here. If we have a lattice here, we automatically will have a real structure on it, because this is just a complexification of the corresponding lattice, right? And then what I claim that this decomposition is completely defined from this filtration. Okay, but just by this rule. If we have a filtration with this property, then we can восстановить. Then we can recover the decomposition. And yes, it seems to be. It seems that we need to take lattice. Okay, and so here we obtain two equivalent notion of Hodge filtration and Hodge structure, but sometimes it's more natural to use Hodge filtration. For example, when we consider variation of Hodge structure, in fact, if you will work with this stuff, you will work with Hodge filtrations. Okay, and now let me illustrate why. Let me state some general things. So first of all, let me state a very famous Hodge conjecture. Do you know this thing? Okay. So what is Hodge conjecture? Yes, of course, as I said, the most important example of Hodge structure of weight n is cohomologies of smooth Kähler variety. Then we will have Hodge decomposition on. If we have a smooth Kähler variety, then we have a Hodge decomposition on its cohomology.
Is it true that there is no torsion in cohomology of Kähler variety?
So if we can see, no, there is torsion, but for Hodge decomposition we take complexification. So the Hodge decomposition doesn't work with Hodge decomposition work with. So as I said, we work with integral or rational. When we work with irrational cohomologies, there is no torsion, right? So Hodge decomposition doesn't work with torsion at all because this is a complexification. Okay? Of course, on integral cohomologies, sometimes there is torsion, but it doesn't matter. Okay, and now let me state Hodge conjecture. So first of all, suppose we have a closed variety X, and we have a closed analytic analytic subset of codimension K. Then we can consider its so-called fundamental class. I will not explain all these constructions very accurately, just because to explain them we will need one more lecture, and I think that in the course of complex geometry of Pasha Osipov, he will explain all these things.
Is it any complex variety or Keller, compact?
It can be even non-smooth. So here we didn't. We just should consider analytics a subset that is closed, and analytic means that locally is given by zeros of sum of k. Here, if we have codimension k, then locally it's given by zero locus of k holomorphic functions. Okay, this is what is analytic subspace. When we consider algebraic varieties, we consider closed algebraic cycles. Okay, this is a irreducible subschemes of codimension.
If we don't require X to be compact, then there can be no fundamental class, right?
Okay, let me here. Okay, here maybe we should ask compact, but what I say is that here we just we can take even non-smooth. A fundamental class is defined even for non-smooth analytic subspaces. Okay, then we can define its class, and in fact, if X is Keller, then it's easy to show, if you will work all the details, that its image in the complexification of this homology lies where? Do you know? In what part of Hodge decomposition this will live?
HKK?
It will always live in this part of Hodge decomposition. So we just consider its image in complexification under an obvious embedding, and then its class always lies here. And a very famous conjecture, so-called Hodge conjecture, for a smooth and projective variety over complex numbers. The subspace of HQ with rational coefficients spanned by all algebraic classes coincide with the space of Hodge classes. Coincide. Of Hodge classes. So that is spent by algebraic cycles. maybe some comments here. It's important that the variety is projective. So for Keller variety, it doesn't work, and even it's possible to construct examples even in complex tori. So it's possible to consider a complex story such that the Hodge conjecture fails. And here it's important that we consider rational coefficients. For integral coefficients, it fails. But I can't very briefly explain why. It's more subtle. I can say this in a few words. Okay, and also let me say that for one classes, this is true, and this is one Lefschetz theorem that we have already discussed, right? Lefschetz theorem. Okay, so for one classes, this is one Lefschetz theorem, and we have already proved it. Okay, and now I want to discuss polarization, but okay, let me define polarization on Hodge structures. Then I will say why its abstract notion is something is related with the projectivity of variety, and then we will see what we will have time to discuss. Okay, polarization. So first of all, let me say that. So let me define Weil operator C that acts on VPQ by multiplication by I, complex I, in the degree pi minus q. Note that C preserves the real vector space VR intersection of VPQ. So real vector space is when we take here a vector and then its conjugate. This is a this is a real subspace here, and it's immediate that Weil operator preserves this subspace. Okay, then definition. A polarization of a rational Hodge structure of weight n. This is the following thing. So we should take tensor product of V times V. This is a Hodge structure. And then we consider Tate Hodge structure twisted by n as me. So we claim that this is the following thing. So this is a morphism of Hodge structures such that
what was that on the right hand side? Q minus n.
Q minus n, yes. Tate Hodge structure that we defined before. So morphism of Hodge structure such that its pair are linear extension form. Maps to on intersection of R and Q. As I said, we have this VL operator preserves this thing. So this is something that lives in this real subspace, and we ask this thing to be positive definite symmetric form. I need to let me just remark that positivity here is important because when we will work with cohomologies of Keller variety, this positivity will ensure that will gives you something ample. So this positivity will gives you an embedding in projective space. So in fact, maybe if you before saw polarization, you know that polarization is something about ample class, right? This is something about embedding in projective space, right? I will not explain why this abstract notion in fact gives you an embedding in projective space, because this is something from course of complex algebraic geometry. But I will just mention that this is something that is that comes from positivity here. Okay. Okay. And if polarization exists on a Hodge structure, we say that the corresponding Hodge structure is polarizable. Okay. And
that's a morphism of Hodge structure of weight 0.
Yes, this is a morphism of Hodge structure of weight 0. Okay, and now let me let me say something about properties of this notion. So, first of all, phi defines on V bilinear period. And for its C linear extension, we have the following thing. If we take P2, Q2, then it maps to C, and this is 0 for all P1, Q1, P2, except for P2 plus P1 plus P2 equal to N and Q1, Q2 equal to N. Okay. Then properties. So first of all, if N is even, then phi defines symmetric bilinear form. If N is odd, then phi is Q-symmetric. Okay, it's the restriction of its C linear extension yields a non-degenerate pairing on PQ, QP, non-degenerate. The third property is that we have a sub-Hodge structure. Sub-Hodge structure. Then a polarization here defines a polarization on V prime. Polarization on V defines polarization on V prime. And for polarized, let me just comment because we don't have time. If these two Hodge structures are rational, then so suppose that this is a polarized Hodge structure, then V prime is also polarized, then so for rational, in fact, for rational polarized, we can also decompose V Hodge structure V in the direct sum of V prime plus V prime orthogonal. And this is an orthogonal complement of V prime with respect to psi. Orthogonal complement. So what I'm saying is that if we have a polarized Hodge structure and a rational Hodge structure and the substructure in it, then we can always consider the direct sum decomposition of V as in linear algebra, right? If we have a form, we can consider canonical direct sum decomposition. For integral Hodge structure, it's not true that this coincide. We have just an embedding of this direct sum here, and this is something, a lattice of finite index here. But for rational, we can always consider this decomposition. Okay, and now let me also comment why this notion of polarization gives you something about projectivity. So to obtain a polarization on Hodge structure of Kähler variety, we should take a Kähler class, a rational Kähler class. Kähler class omega of a Kähler variety X. So there should exist a rational Kähler class, and in fact, this will give you a polarization. And to explain accurately why I need to write down some Hodge-Riemann pairing and so on, and I don't want to do this, but let me just leave it in such a form. So we should take a Kähler class, and in fact, if we have a rational Kähler class, then the corresponding variety X is projective, and this is something that is called Kadeira embedding theorem. Kadeira embedding theorem implies that X in this case is projective. So Kadeira embedding theorem says that if we have such a rational Kähler class, then there exists an embedding of X into projective space. Okay? So this is why this abstract notion corresponds to predictivity for our favorite Hodge structure. on a cohomology of Keeler variety. Okay, and sorry, this time we don't have time. This lecture we don't have time to illustrate why all these notions are important. But next time I will illustrate it. I will just formulate Tarelli theorem for curves. So next time we will discuss Hodge structures of weight 1 and of weight 2. So we will discuss why integral Hodge structure of weight 1 is the same thing as complex tori. Then we will mention that in this bijection, polarized Hodge structures are in bijection with abelian varieties. That is a complex stories that have that are projective, that are algebraic. We will state Tarelli theorem for curves. That is a statement that we can that two curves, two compact complex smooth curves are isomorphic if and only if there is an isomorphisms of Hodge structures on their first cohomologies that respects just intersection pairing. And we will state, and for weight 2 Hodge structures, we will discuss what we have for K3 surface, what is its Hodge structure, and then we will state global Tarelli theorem that that is about that is a statement that K3 surface is completely determined by its weight 2 Hodge structure. And also we will discuss transcendental lattice, and maybe if we will have time, we will state derived Tarelli theorem that tells you that the corresponding transcendental lattice are isomorphic if and only if derived categories, bounded derived categories of coherent shapes on two K3 surfaces are isomorphic triangulated categories. I was sure that we will have time to discuss this today, but sorry. So I hope that next time I will illustrate why all these things are important. Okay?
Но тут поляризация возникает не на всех когомологиях, да?
На всех, на самом деле. Ну, то есть там сейчас.
Я только на примитивных знаю. Мы же хотим вот какую-то там положительную определенность.
Да. Это да. Я имела в виду, что все предметности. Ну, что это вот?